Alright, welcome back everybody. In this video we're going to look at the last two examples from the Introduction to Riemann Sums lesson. We'll start by finding MRAM sub 5 for our function y equals x squared plus 1. Just as I did in the previous video, I'm going to number my horizontal axis and vertical axis first, and create my sketch of y equals x squared plus 1. So let's see, when x is 0, y is 1, when x is 1, y is 2, when x is 2, y is 5, and there's our sketch of our curve. And just like we did in the previous example when we were dividing this interval into 5 rectangles, we took the width of the interval, which is 3 units, divided into 5 rectangles, means that each rectangle is going to be 3/5 or 0.6 units wide. So I'm going to put some markings down here: 0.6, 1.2, 1.8, 2.4, and 3, subdividing all of these intervals. And now we're finding MRAM, so we're going to base the value off of the height of the function at the midpoints of these intervals. So at 0.3, at 0.9, at 1.5, at 2.1, right about here, and at 2.7 about here. And so the rectangles that we're using to approximate the area are going to look like this. There's the first one. Oops. And the second one. Having trouble getting this rectangle going. Come on. There we go. Finally. And so our approximating rectangles should look something like this. Now, something you'll notice, unlike the examples that we did with LRAM and RRAM, is instead of all the rectangles being above the curve or all the rectangles being below the curve, since this is an increasing curve, what we've got is we've got a little bit of excess area on each rectangle. You know, this right here, a little bit of excess area that's getting picked up by the rectangle. And that's kind of balanced out by the amount of area that's left uncovered by that rectangle on that interval. And as a result, we tend to find that MRAM is a little bit more accurate than our LRAM and RRAM as far as finding the exact areas of the underneath the curve on the interval. Alright, so now I'm going to calculate this. Now we have each rectangle is 0.6 units wide. And then we want the value of the function at the midpoints. So we want the y value at x equals 0.3, 0.9, 1.5, at 2.1, and come on, at 2.7. Okay, so we'll find those values. At y is 0.3, that's at x is 0.3, the y value is going to be 1.09. At x equals 0.9, it's going to be 1.81. At 1.5, that's going to be 3.25. At 2.1, That's going to be 5.41, and at 2.7, it's going to be 8.29. And then we'll add all those values together and multiply them by 0.6, and that's going to give us our MRAM approximation here. I'm going to go ahead and break out my calculator. 0.6 times quantity 1.09 plus 1.81. And we'll just go ahead and add all those together. Oops, missed my 8. And we get 11.91 as our approximation. Okay. Now something that we can do to increase our accuracy when we're using Riemann sums is put more rectangles underneath the curve. So for instance here I talk about using LRAM sub 10 on this same curve that we've been looking at the whole time. And in general, using 10 rectangles to approximate the area under the curve is going to be better than using 5 rectangles. So LRAM 10 should be a better approximation than LRAM 5. And LRAM 20 should be a better approximation than LRAM 10. We would subdivide this function into, it's 3 units wide divided into 10 rectangles. So each subinterval here would be 3/10 of a unit wide. 6.9, 1.2, 1.5, 1.8, 2.1, 2.4, 2.7, and 3. And so we would have all these really tiny, thin rectangles, and let's see how well this works for me, since I already know that I have trouble putting rectangles underneath here already. I think these rectangles just might be too small for me to get underneath here. There's one. There's a second. Third. At least good enough for us to see what's going on. I missed that one a little bit. Let's pull that one back. There we go. And you see with 10 rectangles instead of 5, remember we had LRAM was under approximating the area. And we have a significant amount less area that's not counted now with more rectangles. Of course, the drawback to this is, while this is going to be more accurate, it's also going to be more work to compute. And so, when we're using RAM to approximate, we need to take into consideration a balance of accuracy versus the amount of work that it's requiring to find that level of accuracy. Because I need a lot of Y values. There's my 10th rectangle. So I need to find all of those Y values in order to get the approximation. This is going to be a lot of calculation work. And so we got 0.3 times 1 is 1.09. And with more calculation work like this comes more opportunity for error. Maybe forgetting to list one of these numbers, maybe typing one in wrong. So you've got to take a moment and step back, make sure you typed everything in correctly here in the calculation. And this is going to approximate the area as 10.695. This is more accurate than the LRAM 5 that we found in the last video, but it's also a lot more work. So when you're looking at approximating areas under curves using RAM rectangular approximation, you need to take into consideration both the accuracy and the amount of work that goes into producing that accuracy, especially as we get into the future and we learn additional techniques that will make it, pretty simple to find the actual area underneath this curve without going through all of this. Alright, that's the end of this video on the introduction to Riemann sums. See you guys next time. Have a great rest of your day.